Okay, recording started. Awesome. So maybe we can start with a couple of the questions that we had from the general chat. So I'm gonna read the first one to you, Nick and TJ. Feel free to any of you can answer it. It is, how is data fusion implemented?
So sensor fusion happens at multiple different stages. You saw the one approach the team has been taking is with faster LiDAR, where the idea is LiDAR is a high accuracy sensor. The distance is already encoded in the point cloud, but it's also low density, so it doesn't have as many points as a camera would. So the idea to fuse them, well, there's a couple ways to fuse them. So one way is you do object detection on the camera frame, and then you have, let's say, a bounding box. You can project that bounding box to a frustum, which is kind of like a plane in real life. Many planes in real life correspond to the same area in image. So if you Google viewing frustum, you'll get a better idea of what I'm talking about. And that way, when you project the bounding box into 3D, you're able to look at the point cloud from the LiDAR and get the distance information from there. However, the LiDAR point cloud usually lags the camera because the camera is faster than the LiDAR. So you're going to need to be able to extrapolate the LiDAR point cloud, so kind of predict what a point cloud would look like in the future. And that's where faster LiDAR comes in, where you can use a flow-based model that Sophie presented on and combine that with the camera information to assist in predicting what a point cloud from the LiDAR would look like in the future. So that way you're essentially fusing camera and LiDAR together to get fresh distance information. And from that point onward, you can either do the frustum based distance estimation, or you can do detection directly on the 3D LiDAR point cloud. And both of those approaches are fundamentally sensor fusion because they use information from both sensors. And so does that make sense so far? Does anyone have questions on what I explained? All right.
Yeah, for people who just joined, we were talking about sensor fusion and data fusion in general. Like, if anyone has any other question related to that, feel free to unmute yourself and ask it, or drop in the chat, whichever you prefer.
And now there's another component for perception, which is for drivable space. For drivable space, we can do sensor fusion by, or on the camera, you can do drivable space segmentation, or you can predict the lane lines. In 2D LiDAR and radar, you can get an occupancy grid. You can also get an occupancy grid from 3D LiDAR. And essentially all you have to do is take the intersection of all the drivable spaces from all the different sensors, and that is also sensor fusion. Finally, when we have multiple sensors, such as the cameras, they look, maybe two cameras are able to see the same vehicle, or the LiDAR and the camera are jointly able to detect the same vehicle. On state estimation side, when we do object tracking, our job is also to fuse together the different observations across the different sensors. But now we don't do that in the raw sensor data space, which we were doing earlier, but instead we fuse that in the object pose space. So when we see a car coming, when we see two cars right next to each other, or maybe if they're so close that in theory they would be colliding, probably they're the same car. So that's another way we can do sensor fusion that's sensor agnostic. So essentially different observations just joined together.
Awesome. Thanks, Nick. We have a question from Kiyohide. about the skills required to join the architecture team. So he's asking, I am an incoming SEM student. I have the experience to attend the FSAE team, and my major is mechanical and material engineering. Is it possible to contribute to the architecture team without expertise in the control or program area?
So the architecture team, yeah, well, let me just preface this with the architecture team will slowly phase out over time. So once we pick the concepts, well, the job of maintaining system architecture will fall to the technical team captain. So there won't necessarily be a team. People will actually be working on implementing things. But TJ has a comment on that as well.
Sure. Yeah. I mean that's correct, as Nick said. But as it's a big system, right? And he's from systems SDM program, which revolves around systems. So definitely there will be avenues where there would be different subsystems coming together, and the interaction of those subsystems in the specific car, like perception, planning, controls. Even in controls, there are three different abstractions that we presented. So all those interactions, when they come together, when these subsystems come together, and not only in the same car, but also how like each other competitor will be implementing some similar algorithms. So if multiple cars are traveling, are driving on the same racetrack, there would be certain interactions between those cars, which we may or may not have anticipated in the past. So those interactions would result in some sort of an immersion, some sort of uh, unknown things that may come forward will have to be analyzed when we start integrating all these subsystems together. So systems architecture team and integration team would play a pretty critical role in at a later stage, again, when all these subsystems are coming together.
And also you were concerned about your background. So the team historically has spent a lot of time making sure that people are placed on the right sub team and can learn the background. We have a lot of both internal documentation, as well as we've compiled a lot of educational content and papers that we can give to people when onboarding, that usually within a few weeks one can start ramping up and also making technical contributions.
Yeah, we definitely not expect anyone to know everything when they join. So I would encourage anyone interested to just apply and go through the process. We'll be more than happy to talk to anyone interested. Cool. We have another question here from Anurag. Are vehicle platforms provided by a race series? How heavily are things like vehicle aerodynamics and mechanics regulated?
So the vehicle is provided by the race series. It's an Indy Lights chassis with some features disabled, so there's no push to pass, so it's kind of simpler. And it's being designed by an external team that's not competing in the competition at Clemson University. How the teams are involved in helping guide those decisions is through design reviews and this Slack channel where we communicate with organizers and ask clarifying questions and make sure that collectively they're on the right track. So we also have, actually our team was vital in starting kind of like a consortium of all the teams that want to compete in this Indy Autonomous Challenge, where we kind of get to pull our requests and talk with other teams about the design of the vehicle and the design of the overall competition and provide that feedback to them. So in a sense, there's some things we can control and some things we cannot control, but the vehicle is standardized. So all the teams will be using the same car. So the only differences will be sensor configuration in terms of frame rate and global shutter and so on, and the software. Vehicle aerodynamics and mechanics are also regulated, so we are not able to change stuff like tow. We're not able to remove the wings or add the wings or like modify the wings.
Cool. Thank you, Nick. We have a great question from Dustin here. I hear you guys talk about LiDAR and cameras. Did you have plans to use radars? Also, what kind of cameras and lidars are you using? I work with Aptiv and work with lidars before.
Yeah, so we've also worked with lidars before. We've done an extensive evaluation of Velodyne lidars, Hesai lidars, Oster, and we're quite familiar with all the different paradigms. However, we don't get to design this car, and cost is a factor for the competition organizers. So the sensors that the competition organizers selected are a VLP32C 3D LiDAR and Ibeoscala 2D LiDAR, macro cameras that do 37 FPS at full resolution and can go up to 60. They have global shutter, so they're not that bad. And finally, there's Aptiv radars. There's four Aptiv radars. Our plan for using the radars is twofold. One is so if we are resource constrained, we will not use the radars. If we have extra time and enough person power, we'll be using the radars first to create an occupancy grid for collision avoidance. Radar is nice because it's a bit faster than LiDAR. It's going to be running at 25 hertz. So we'll be able to get some collision avoidance information. Maybe we could also use the Doppler effect information, such as like local velocity and so on, to make that occupancy grid a bit more dynamic. And the second thing we want to investigate is, can we use radar and fuse it with the cameras to get depth for our image space detection? So when we have a bounding box in the camera space, can we get the depth of that bounding box using radar? We'll be looking into this. It really depends on whether there's overlap between those two spaces, and if we can calibrate those two sensors together, or use a model like neural network depth estimation that's augmented with this radar data.
Awesome. So I think we have one more question from the broader chat. It was a very general one. Are you working with any actual indie teams to develop the driving strategy algorithms?
So we did start the Indie Autonomous Challenge Teams Consortium, where in the beginning, we're trying to make this competition a bit more collaborative before people start specializing in different directions. The main collaborations we have extended so far across most of the teams that are competing are making sure the organizers are on the right track with what we believe that are the requirements for a successful competition, and putting together a list of requests, and just in general communicating with the organizers as a group. Other things that are ongoing right now are we have open access among each other for simulation interfaces. So kind of filling in some of the gaps from the competition organizers, and providing some of that tooling that we want to share. For driving strategy, I think this will be a thing that will come up after a few months. So on a recurring basis, we have these hackathons where we get to compete in simulation with other teams, and there we'll be able to see, once the first multi-agent simulation happens, are the vehicles crashing into each other? Do some teams not have collision avoidance, and so on? And perhaps what we could do there is either help them implement some base collision avoidance, so that they don't crash their car come the actual competition day. And also for our own side, if we can detect which team corresponds to which car from the perception standpoint, we know to be more careful around certain cars, or like leave wider margins, or not cut in front of them, because we know they'll probably crash into us. So that's where I think some of that emergent emergent behavior TJ was referring to earlier for planning will come into play and will be quite important in making sure we don't crash a $400,000 car.
Yeah, yeah. In addition to that, I mean, there were a few questions on adversarial behavior of the competitors. In addition to our software stack and the software stack of other competitors, the Deep Orange network, the Clemson team that is designing the vehicle, they would have a way to control the vehicles remotely. So in cases where some team may be intentionally messing things around, they can definitely take control of that vehicle and transition that vehicle into a power limited operation or something like that.
Awesome. Thanks to you, Nick. A couple more questions here. One from Justin. Does a race require teams to be concerned with racing in inclement weather, mainly rain?
Well, they'll probably, if it's raining, they'll probably ask us, are you comfortable racing in rain? And we'll probably say no, because it's dangerous and we're not going to be doing testing. Like there's very few testing days. There's 4 testing days on the actual racetrack where, most likely it's not going to be raining on those testing days. So we'll have no data for how does this car behave on wet tires and rainy surface. So
yeah.
and also we'll probably not have training data.
Just to add to that, I think that normally racing, like professional racing series in ovals, like for example NASCAR, I believe it's the same for IndyCar. They don't usually race on rain, just because it's very, again, very hard and also it's not safe. So yeah, we'll most likely be racing in dry terrain.
However, there's an important aspect, which is making sure the perception models work under different lighting conditions. So when the sun is shining in different directions and so on, different times of day, if there's postponing of the race like a few hours and so on. So we'll have to take that into account, perhaps with data augmentation or just getting a better data set overall.
Awesome. Question from Dustin. How fast are you guys targeting these vehicles to go?
Sure, yeah. So yeah, the top speeds would be around like 200 miles per hour. Average speeds around 160 to 180 miles per hour. So it's pretty fast.
And the thing is that we're racing on an oval. We're asking a professional Indy Lights driver, how do you race on an oval? And he's like, oh, you just step on the gas pedal and then you steer. So basically, you never really have to brake unless you've made a big mistake and you want to try to get out of it. Which means that effectively you're just modulating how much you're stepping on the gas. So that's why we're able to go so fast. However, and also to be able to race in a head-to-head scenario, you have to prove to the organizers by actually racing on your own if you can hit certain top speeds, because we don't want cars that cannot go above 40 miles an hour to be racing with cars that can go 180 miles an hour.
If I'm not mistaken, Nick, I think that we actually need to prove that we can average 120 miles an hour on the qualifiers, right? Before actually making it to the final race. So 120 miles an hour average would be sort of our minimum speed, but yeah, we're definitely targeting above that. Cool. We only have a couple minutes left, so we don't have any more questions in the chat, but if anyone wants to ask a final question, please feel free to unmute yourself and just ask it. We'll be very happy to answer any additional questions while we finish in a couple of minutes.
Hi, Jorge. This is Jim Quisenberry. Could you take a minute or two and explain your general approach to safety of the system and how that may have changed when you're introducing multiple actors into the same field of view now?
Sure, I can take that. So we are considering safety. So from the Formula Student racing, where there were no other agents, safety was minimal. It was just having our car not crash into the cones or crash into the go off track. Here with other vehicles into play, we are taking a top-down safety approach where instead of looking at each and every component and analyzing safety or hazard analysis, doing a hazard analysis for that particular component. We are thinking about doing a system safety analysis where looking at the system from top down, where the system is your car as well as all other cars, and how do these cars would interact with each other when they are traveling at 180, 200 miles per hour, in scenarios where people may intentionally do bad things, and intentionally they may want to collide their cars with other cars. Even those scenarios are theoretically on paper possible. So looking from that level, and then going down deeper into how do that dissect into how the perception, planning, and control subsystems should react to such kind of hazards, and should implement failure mitigation strategies in case these hazards happen. So that's an overall approach that we are trying to take here. But that will, like from a technology standpoint, that would mean we'll have to put in place a lot of safety nets and a lot of algorithms where, in case we think that it's not safe to go on a particular trajectory, we have an alternative trajectory to go to. We have some way to limit our speed, or do a maneuver which is safer, or gracefully quit, in the sense that go out of the track and then stop there instead of colliding into other vehicles. So all these like top level hazard analysis brainstorming sessions would lead into developing algorithms, developing logic to mitigate those failure modes.
That's a very nice approach. Thank you for explaining it.
Thank you.
Awesome. So we're at time. Well, I would just want to thank everyone. Thanks, Nick and TJ, first of all, for answering all those questions. And thanks, everyone, for joining our event today, and also for joining our breakout room. We're very excited to have so many people show up and share our progress with anyone. If you have any additional questions or want to reach out to the team, in the chat box, you can find both our application link as well as our email, where you can email all the team and with any general questions, concerns, or sponsorship interest. So we're more than happy to receive any message from you guys. But other than that, we're very happy to have you here, and thank you so much for joining.
Thank you, and best of luck to you.
Thank you.
Thank you.
Bye, everyone. Cool. Thank you, guys.